Okay, let's get started. Welcome to the 11th session of SIGCOMM 2021, and we are going to talk about what networking can do to make machine learning faster and more efficient. And we have 3 papers today, and they range from designs that changes hardware, that focuses on designing new algorithms and new software systems. And I am Mosharraf Chaudhary from the Big House at the University of Michigan. And our first paper is going to be Hoplite. We have 2 presenters today. One is Siyuan Zhuang, and the other one is Zhuohan Li. Siyuan is a CS PhD student at Berkeley. He's advised by Don Song and Ion Stoica, and Zhuohan is also from Berkeley, where he's advised by Ion Stoica. And they're both interested in systems for machine learning and large-scale distributed systems. Yeah, let's hear the talk.
Hello everyone, I'm Johan from UC Berkeley Rice Lab. Today, Sue and I will present our recent work, Hoplite, Efficient and Fault-Tolerant Collective Communication for Task-Based Distributed Systems. This is a joint work with Danyang Zhuo, Stephanie Wang, Eric Liang, Robert Nishihara, Philip Morris, and Jan Stoica. Task-based distributed systems have become increasingly popular for implementing distributed applications with asynchronous and dynamic patterns. Today, many companies have started to adopt task-based distributed frameworks. For example, Ant Financial uses Ray to run their online machine learning pipeline and serve financial transactions that worth billions of dollars. In task-based distributed systems, an application is decomposed into multiple tasks. For example, a reinforcement learning application can be divided into a training task that
So we are having some technical difficulty. Hopefully it will be fixed soon enough. Let's go.
Hello everyone, I'm Johan from UC Berkeley Rice Lab. Today, Sue and I will present our recent work, Hoplite, Efficient and Fault-Tolerant Collective Communication for Task-Based Distributed Systems. This is a joint work with Danyang Zhuo, Stephanie Wang, Eric Liang, Robert Nishihara, Philip Morris, and Jan Stoica. Task-based distributed systems have become increasingly popular for implementing distributed applications with asynchronous and dynamic patterns. Today, many companies have started to adopt task-based distributed frameworks. For example, Ant Financial uses Ray to run their online machine learning pipeline and serve financial transactions that worth billions of dollars. In task-based distributed systems, an application is decomposed into multiple tasks. For example, a reinforcement learning application can be divided into a training task that maintains the policy and multiple rollout tasks that interact with the training environment and provide updates for the policy. Note that different rollout tasks have drastically different lifetime. Some end shortly due to a bad initial state, while others last long with a good policy. Therefore, rollout tasks are often being created dynamically at runtime according to the results of previous rollout trails. After defining the tasks for the application given a cluster, the task-based distributed system schedules the dynamically created tasks to the workers on different nodes. Also, it handles the communication between task workers. Finally, when a worker fails, the system can reschedule the task to another worker and reestablish the communication with other tasks. Therefore, the failure of a single worker will not lead to the failure of the whole application. For many distributed applications, the communication between different tasks actually forms a collective communication pattern. For example, in the IO example, the training task will broadcast the same policy network to all raw tasks and reduce the average results from the raw tasks to update the policy network. More specifically, a collective communication involves a group of participants and follows some specific pattern. These patterns include broadcasts from one member to all members of a group, reduction of values from all members to a single value with operators like summation, and the OnReduce pattern that distributes the reduced result back to all members. In current task-based distributed systems, there is no optimization for these patterns. For a broadcast, the sender just sends the object to all receivers one by one, whose speed is bottlenecked by sender's bandwidth. Note that there are many existing works on optimizing these communication patterns. One popular library is MPI. For example, to start a broadcast in MPI, all the participants need to call the MPI broadcast API together. Then MPI will produce a static schedule to perform the communication. For example, here, after receiver 2 gets the data from the sender, it can act as another sender for receivers 3 and 4. This reduces the burden of the single sender. However, those traditional libraries are not feasible for task-based distributed systems. First, for those libraries, all participants should be known before a communication, and the communication schedule is static. This is not compatible with task-based distributed systems, where the receiver tasks are created dynamically. In addition, if receiver 2 fails, receivers 3 and 4 will not be able to receive the result and proceed. This will break the fault tolerance feature of task-based distributed systems. Therefore, our challenges are to provide efficient collective communication with dynamic tasks, and we should also allow tasks to make progress on collective communication, even if other tasks have failed. Let's first take a step back and see how these tasks communicate with each other. In most systems, the task communicates through a distributed object store. Specifically, the object store includes a local object store on each node and a global shared object directory. If a task on node 1 wants to send an object X to node 2, it will first call put X to write the local object store. And after that, it registers the object in the global distributed object directory. On the receiver side, the receiver will first check whether the object is in its local object store. If not, the receiver will query the global object directory for the object. After the receiver gets the sender's location, receiver's local object will start receiving the object from sender's local object store. And finally, the object will be returned back to the receiver for further execution. Therefore, we build Hoplite as a distributed object store underlying task-based distributed systems to enable efficient collective communication. We provide very similar APIs compared to a key-value store with an additional reduce call to specify the objects to reduce from. With previous APIs, to perform a broadcast communication, the sender only needs to call put, while the receivers can call get at any time. To perform a reduce, the reducer calls the reduce call to specify the objects it wants to reduce from. Other collective communication primitives, like OnReduce, can be derived by a combination of broadcast and reduce primitives. To enable efficient collective communication, we design Hoplite on top of two main key ideas. First, we compute data transfer schedule on the fly and transfer data with fine-grained pipelining. Second, we dynamically adapt the data transfer schedule to alleviate the effects of the failed task. Next, Suyuan will talk about how does Hoplite uses these two key ideas to design the algorithm for collective communication.
Hello everyone, I'm Suyuan. I will introduce Hoplite's algorithm part. This is the architecture of the task-based distributed system shown earlier. Hoplite modifies the logic of the object directory and each node's local object store. For example, with the original object directory and the local object store, S broadcasts the object to the receiver nodes one by one. With Hoplite, receivers form a more optimized broadcast tree dynamically and pipelines data between nodes. Now, we show how broadcast actually works in Hoplite. Assuming we are going to broadcast an object from S to other nodes R1 and R2. First, R1 and R2 ask the object directory for the object. Since there's only one sender for the object directory tells one of the receiver R1 to get the object from S. Then S starts sending the object per R1's request. One important observation is that once R1 receives partial data from S, R1 can register as a new sender. Then the object directory tells the pending R2 to receive the object from R1. Similarly, R2 can serve as a sender. As it goes on, S pipelines its object to R1, and R1 pipelines its partial object to R2. Now, S has finished sending the object, and R1 has also sent part of its data to R2. Since S has finished, S registers itself back as the sender. Now, let's say we have two new receivers, R3 and R4, querying for the senders. The object directory passes two senders and two receivers for data transmission. In the end, all workers get a complete copy of the data and register as senders. With this algorithm, Hopelite efficiently handles the dynamic request and maximizes the bandwidth for data transmission. However, what if there's a failure in the system? Back to the previous step where we are pipelining data from S to R1 and R2. Say that R1 fails suddenly and disconnects from S and R2. R2, the receiver of R1, reports the incident to the object directory. S, the sender of R1, becomes available again. Then R2 asks the object directory for a new sender and resumes receiving data from S. Then let's talk about reduce. Unlike broadcast, reduce depends on both the number of objects to be reduced and the candidates who hold these objects. For example, we want to sum 3 objects out of the 5 candidates. Say that R1, R2, and R4 are the first 3 ready candidates. Then the result is the sum of the objects from R1, R2, and R4. Say we have one node, R0, asks for reducing 5 objects out of 6 candidates. Then the object directory builds a reduced tree with 5 nodes as placeholders for 5 objects. The upper green blocks represents the objects to be reduced, and the lower yellow blocks represents the reduced data. The object directory fills the placeholders by in-order tree traversal order. Say that R1 and R2 are already first. R1 is a leaf node, so its reduced object is the same as its own object. R1 starts pipelining reduced state object to R2. Then R3 is ready with the partial object and also pipelining to R2. R2 reduces its own reduced object with data from both R1 and R3. This process continues, and we work out the initial reduced object for the root node R4. Say that suddenly R2 failed and disconnected. Then R4, the receiver of R2, reports the incident to the object directory. R4 also resets the progress of the reduced data. Because there are 5 objects out of 6 candidates to reduce, we can use the extra candidate R6 as a backup. When R6 arrives, the object directory informs R6 to replace R2 in the reduced tree. Then reduce continues. We conduct several experiments using Hopelite. Distributed reinforcement learning is becoming more and more important nowadays. We integrate Hopelite into RayRLib and evaluate 2 popular IO algorithms, Impala and A3C. Hopelite shows superior performance than the original RayRLib for both algorithms. An important use case of task-based distributed systems is to serve a wide range of machine models implemented with different frameworks. We evaluate Hopelite with RayServe, a framework-agnostic distributed model serving library built on Ray. We benchmark model serving with an ensemble of state-of-the-art models. Hopelite significantly improves the performance of model serving because of more efficient input feeding of the model ensemble. Finally, we evaluated the ability of Hopelite to recover from failures. We introduced worker failures in the ML serving experiment. Hopelite is not only consistently more efficient than the baseline, its failure recovery is as rapid as Ray. Today we present Hopelite. The key idea of Hopelite is that we compute data transfer schedule on the fly and transfer data with fine-grained pipelining. And we dynamically adapt the data transfer schedule to alleviate the effects of the failed task. With Hopelite, we can increase the communication efficiency of emerging applications built on task-based distributed systems while preserving the dynamic communication pattern and fault tolerance. That's all. I'm really happy to share the paper with you today. Feel free to ask any questions.
Okay, thank you for an excellent presentation. And I'm looking up the questions on Slack, but before that, I have an obvious one. I'm sure you are aware I spend too much time working on problems that are similar. So the obvious question is sort of, how is this different from like all the works that's related to CoFlow?
So if I understand correctly, so the question is about how the hoplite differs from traditional collective communication libraries. So I think the biggest difference is that we work on the task-based distributed systems, which inherently by its design is very dynamic. So all the tasks and all the participants of the collective communication are joined dynamically. And so, but like for traditional collective communication libraries like MPI, you need to know all the participants for a communication beforehand. And another important feature about task-based distributed systems is about the fault tolerance feature. So like, even if like a single task fails in task-based distributed systems, we like the whole application should be continued to run. It's like with it like looks like there is no fault. But like for MPIs, where like for those traditional collective communication libraries, most of them are designed for supercomputers. And then in that case, it's like they basically provide very limited fault tolerance technology. And so I think the design of hoplite is to basically to get the efficiency from the collective communication, traditional collective communication libraries, but also to provide like some good, like nice features like dynamic task and fault tolerance from task-based distributed systems.
Thank you. I also have another question on the Slack. Well, I mean, I guess it's an answer, right? Yeah, actually, this is a question. So it's from, I'm just trying not to mispronounce Jolon. And he says, great work and great talk. Did you consider the case where both computing resource of the nodes and network bandwidth of the nodes links are not equal or uniform or matched? How do you build the transmission tree in that case?
Yeah, so I think in hoplite the currents we only consider that the communication, I mean the bandwidths are the same for all the nodes. Yeah, that's actually true in our evaluation, and for most applications running in the cloud. Yeah, so that's definitely a very interesting question for further research. Yeah, because because it could because it could be interesting to know how to implement a more collective communication with some non-uniform narrow bandwidth.
Okay, and on that note, I sort of had another question that's related to the fault tolerance. Like the numbers you showed, it seemed like even without hoplite, Ray was, I don't know, coming back as quickly. So I mean, what was the key takeaway of that fault tolerance mechanism? Because the design you presented, it didn't seem like it's, I mean, something that should add additional overhead. No, I mean, it's sort of very well explained. And so, like, is that the best we can do, or should we do something else, or should we find that it's as good as Ray in terms of fault tolerance?
I think in most cases, the only thing you can, especially in task-based systems, the best thing you can do is as good as Ray. For example, a process or task just fails, and the best thing you do is that you just detect the error and restart that task, and the task rejoins basically your application, and that's both Ray and hoplite do in its application. So we show that as comparable is comparable with Ray. It shows that hoplite is very efficient for handling fault tolerance here. And the most important thing is that because hoplite makes use of something related to collective communication, And in some traditional connectivity communication systems, you cannot recover from failure. So the time latency could be infinity long, or you have to restart your application. Yeah.
Okay, thank you so much. And also, again, sort of, this is a very good work. And let's thank the speakers, I guess, with our mics off. And let's move on to the next talk. So our next talk is going to be on hardware design. As I promised that we are going to talk about new hardware as well. And the paper is SIP-ML. I'm guessing it's pronounced SIP and not SIP. I apologize if it's SIP-ML. But regardless, the presentation will be by the final year PhD student at MIT, Mehrdad Khani, who is advised by Muhammad Ali Zadeh. So Mehrdad is interested in computer networks and applied machine learnings. And in this work, he's going to talk about sort of how to use optical networks for making machine learning training faster. And after the talk, we're sort of very sort of fortunate to have hopefully both Mohammed and Mania also online to answer our questions regarding the work. Mehrdad is sort of, due to some family issues, he probably won't be able to sort of join us for the Q&A, but he will be missed, but we'll have other people to answer questions. So please ask questions in Slack.
Hello, everyone. I'm Mehrdad, and today I'm going to talk about Supermod, a system that uses silicon photonics and optical network interconnects to accelerate machine learning training. This is joint work with Mania, Mohammed, and our collaborators at Columbia University, Google, NVIDIA, and Protopia. Machine learning workloads require massive amounts of bandwidth. This graph here shows the InterGPU communication bandwidth across different generations of NVIDIA's NVLink interconnects. In the last 5 years, these systems have seen a rapid increase in bandwidth, with the latest generation reaching 2.4 terabps of InterGPU bandwidth. There are two main drivers for this increase in bandwidth requirement. First, ML models continue to rapidly grow in size. State-of-the-art models often don't fit on a single GPU and must be split across many GPUs for training. This is called model parallelism and has a high communication overhead. Second, large batch training, a technique used to reduce the communication requirements, is hitting its limits. ML training involves repeatedly computing model gradients over batches of training data and updating the model. The idea in large batch training is to increase the batch size with the system scale. This ensures that each node has to do a lot of computation per iteration. And since the communication per iteration does not depend on the batch size, this approach effectively reduces the required bandwidth. Large batch training is the main approach for scaling ML training in large clusters today. However, it cannot scale indefinitely. Beyond a certain batch size, training algorithms converge less efficiently, and the overall training time does not reduce. To reduce the training time without increasing the batch size, we must complete each training iteration faster. This is called strong scaling and requires increasing amounts of bandwidth as the system scales. Today's network infrastructures, predominantly based on electrical packet switches, cannot deliver the needed bandwidth for future ML workloads. Here we show a canonical ML cluster today. We have high bandwidth systems like NVIDIA DGX that provide terabps of InterGPU bandwidth. But anything beyond one system must use standard data center Ethernet or InfiniBand networks that only provide gigabps per node bandwidth. On the other hand, optical networks can easily deliver terabps of bandwidth between a large number of nodes. In fact, silicon photonics technology promises order of magnitude higher bandwidth density than conventional electrical I/O interfaces. And optical interconnects can support virtually unlimited bandwidth if a path exists between a source and a destination. However, Optical networks are circuit-based. To communicate, a sender must have established circuits with its receivers. And there is a limit on the number of active circuits per node that translates to how many destinations it can talk to simultaneously. We call this the degree constraint of the interconnect. In addition, reconfiguring circuits incurs some latency. With every reconfiguration, we have to wait until the new circuits become stable. Depending on technology, this can take anywhere from several microseconds to tens of milliseconds. In this project, we developed Supermod, an end-to-end optical solution for ML training clusters. Supermod uses SIP chiplets and all optical interconnects to deliver terabps of bandwidth to thousands of GPUs. And it reduces the training time by up to 9x compared to existing systems. Supermod is applicable to a broad range of circuit switch interconnects, and it overcomes the communication degree and reconfiguration latency limitations of circuit-based networks. The key insight behind Supermod is to exploit the structure and predictability of ML training to tailor the workload to the optical network characteristics. We consider two instantiations of Supermod, which span two ends of the design space of optical interconnects. The first, called SIP-OCS, uses standard optical circuit switches that are commercially available today. These OCSs can support any permutation of circuits, but they have a 30 milliseconds reconfiguration latency. For most training jobs, this overhead is too high to reconfigure circuits within a training iteration. Therefore, for SIP-OCS, we focus on one-shot configuration of circuits for a training job. Our second design, SIP ring, places the nodes along a fiber ring and uses a SIP device called microring resonator for assigning wavelengths to different flows along each segment on the ring. On a ring, it is preferable to communicate with nearby neighbors since the same wavelengths can be reused for different flows that do not traverse the same ring segments. On the other hand, unlike the OCS, the microring resonators can be reconfigured very quickly, which is within 20 microseconds in our measurements. Hence, for SIP ring, we allow dynamic circuit reconfiguration throughout the training job. The core component of Supermod is an algorithm for parallelizing the training job over a set of GPUs. And this parallelization is done such that, in a way that the training time is minimized and the network degree constraints are also met. Let me describe this algorithm using an example. Here we have a, say, 4-layer model given as a compute graph that shows the operations in layers and their data dependencies. So op A here has to be executed before op B and so on. Suppose our task is to split these ops across 4 GPUs. And the constraint is that no GPU can communicate with more than 2 other GPUs during the training job. So the first thing we are going to do here is to split the ops in this compute graph into smaller units called sub-ops, and we actually place these sub-ops across the GPUs. This gives us what we are going to call a balanced compute graph, where every sub-op takes at most a nominal amount of time, for example, 100 microseconds. Now we have to also add back the data dependencies. These are the edges that represent the data communicated between these sub-ops. Now we are going to do a placement across 4 GPUs across time. The goal here is to maximize the parallelism while respecting the communication degree constraint. We translate the degree constraint into a maximum distance that the 2 GPUs can communicate on a conceptualized ring. So GPU 0, in this example, can communicate with GPU 1 and 2. GPU 1 can communicate with 2 and 3, and so on. Let's start placing the sub-ops. Let's place A0 first. A0 can be basically placed anywhere as it is the first op. Now A1 can be placed on any free slots, and there is no data, it has no data dependencies, and there is no communication between A1 and any previous ops. Next, P0, as P0 receives data from A0 and A1, so it can be only placed on GPU 1 and GPU 2, and we place it on the first eligible GPU. Similarly, we continue for C0, C1, C2, and for C3, notice that we can actually place C3 on GPU 0 because the degree constraint forces us that GPU 1 is only allowed to talk to GPU 2 and GPU 3. So we have to schedule C3 on the next time slot on GPU 1. And then we continue this way till all suburbs are placed. So this is the resulting placement that we call a four-way model parallel placement. Now the algorithm that I described can be easily extended to hybrid model and data parallel placement as well. The basic idea is to repeat the same model parallel schedule multiple times and reserve 1 degree of communication for data parallel OnReduce ops. I described this more in the longer version of the talk. Well, let me show you what that kind of hybrid communication pattern looks like. Here is an example of the traffic matrices that this approach creates. In this case, we take the transformer model, split it across 1024 GPUs, and the maximum communication degree of the interconnect here is 16. And I'm showing 3 schedules produced for different degrees of model and data parallelism, going from 4-way model parallel all the way to 16. You can see these block diagonal communication matrices here, where each of the squares in the communication pattern for model shows the communication pattern for model parallel component. And you see most of the intensity is actually around the diagonal. So GPUs are talking more with the GPUs that are nearby. And there is an off-diagonal component for the data parallel part. Once we have the traffic matrix to schedule circuits, basically we have to solve an optimization problem that finds the circuit configurations given the traffic matrix. In CPOCS, this is a one-shot integer linear programming that we solve. For CPRING, it is costly to repeatedly solve the IOP, so we actually provide a fast heuristic. Please see the paper for details of our heuristic. To do our evaluation, we build an accurate simulator for ML training that supports arbitrary models and different optical and electrical topologies. Let me show you some evaluation results. Here we plot Supermod's performance for 3 ML training workloads split across 1024 GPUs. The x-axis in this plot shows the bandwidth per GPU, and the y-axis shows the total training time to achieve a certain level of model accuracy, which we refer to as time to accuracy. Lower time to accuracy is better, and notice the y-axis is logarithmic in these figures. We compare the performance for 2 electrical clusters that use NVIDIA DGX boxes of 8 GPUs connected with 200 and 400 gigabps electrical hierarchies. And we also show the performance for a flat electrical switch, which delivers a full bisection bandwidth in both data parallel and hybrid parallel strategies. And notice that both CPRING and CPOCS perform very close to the ideal electrical switch with full bisection bandwidth. Also, Supermod speeds up the training by a factor of 1.3 up to 9.1x compared to a hierarchical electrical fabrics, which are representative of today's ML clusters. In summary, the demand for network bandwidth is growing rapidly for scaling ML training workloads. Optical networks can deliver huge amounts of bandwidth, but they have their own inherent limitations of degree and reconfiguration latencies. Supermod overcomes these limitations by tailoring the parallelization and placement strategies for optical networks. Please check out our code on GitHub. Thank you.
Thank you. So let's start with the Q&A. I can start. So yeah, I see both. Mani and Mahmoud Aman. Hi, guys. So at a high level, I was wondering about like the algorithm, the way the example was presented, it started from the left and it went to the right, like across layers. Is it possible that when you are trying to place something, it also depends on what is to the right? Because it seemed the assumption was that like only what happened as you go, like layer by layer, only the prior layers matter. But I feel like at least it seems like there should be cases where you end up in a corner and you cannot really go back because you have placed something in the past in a certain way and the future, that's why it's always going to be worse than whatever could have been, because like you have already pinned yourself in a particular corner. Like how, I mean, is there, is this what it is, or like we can have better algorithm, optimal algorithm, or what are you?
Yes, very, very good questions. Great question. So one step, so I mean, the example that Mirvat showed is this really simple sort of linear example. But one step for a general computation graph before running this algorithm is to do a topological sort. Mm-hmm. In general, it's a DAG. You do a topological sort, and then you go from parents to children. Mm-hmm. And when you do that, one pass almost like in the majority of cases, one pass does actually give you an answer that's feasible. There are situations where exactly what you said happens even then, that you keep going, and as you go to the end, you get stuck. Then it's sort of one of these algorithms where you kind of you go back, you correct locally, and then you keep going forward. And then that doesn't sort of after like a finite iterations like this will actually give you yield an answer. But by and large, if you start with a topological sort and process nodes in that order, these things where you get stuck are all local phenomena. Like you might get stuck in between two layers, but it's not a you have to like redo your whole placement.
Got it. Thank you. I have a question on the chat from Amedio, who's saying, how do optical interconnect and silicon photonics compare with electrical switches in terms of cost per BPS? Do you expect the cost to improve in the future with the economy of scale?
Thanks for this question, Amedio. Great question, and the answer is yes, certainly. That's sort of the beauty of this paper. We are looking forward into the world where silicon photonics becomes available on a GPU level. But what's really nice is that at the FPGA level, there's already companies like Intel and startups that are putting silicon photonics optical I/O on an FPGA. So soon enough, we're gonna see FPGAs with 10 terabits per second I/O coming out of it. And so the more with the economy of scale, as you mentioned, we're gonna see the cost of these silicon photonics optical links to go down. We do have a table in the paper that actually compares the cost of these interconnects. And even with today's costs, we are sitting at a cost advantage. It's actually a very interesting thing to think about, that because we can build a better interconnect, not over provisioning, not having to waste a lot of bandwidth, that we win on cost.
Thank you. I have another question which was asked by Ray Yuang, but I actually also thought about it like when I first read the paper, is sort of, could you speak about recovery from GPU failures? It seemed like the design is very sort of highly optimized, almost like supercomputing type world, that the earlier paper was saying that as we move to commodity, things are dynamic and changing and failing, and we have to adapt. How does it sort of handle or work out in the context of this changes?
Yeah. Great point, Musharraf. I think my initial answer to this question is what we do today to recover from failures is redundancy. And so we do need to allocate some redundancy, maybe redundant ring of fibers to every other GPUs, so that if one GPU fails, our fiber ring is not disconnected.
Got it. So I have one last question before we move on. It's from Aditya. With ML clusters going sort of multi-tenant, have you considered how your approach could be extended to such multi-tenant settings? Like, I would think that Aditya would think that the dynamics brought upon by multi-tenancy may render your approach suboptimal. But there are several other interesting issues to consider as well. But I mean, in general, your thoughts on multi-tenancy and this type of very tightly integrated high performance design, like how do they coexist?
Also, another good question, Aditya. I think multi-tenancy actually makes the problem more interesting for us because we have the granularity of wavelengths. And now I can allocate a wavelength to one tenant. And so I would say makes it more difficult, but we also have a degree of freedom at the wavelength level. Mohammed, would you like to add anything?
Yeah, I mean, we've sort of, we've thought about how do you build a cluster that supports multiple jobs concurrently, and but without really sharing. I mean, without sharing, it's sort of the same problem. You know, you have a set of GPUs. Preferably, you'd place those GPUs, like if it's on the ring, the SIT ring design, you place them sort of close to each other, and then the rest of the placement algorithm essentially runs, you know, job by job. And exactly the same idea kind of holds. It's just different subsets of GPUs being used for different jobs. Mm-hmm. If you need to share GPUs, I think I do think that's a whole set of sort of interesting new problems that
Got it. Yeah.
I'm going to look at.
Yeah, it is indeed. Thank you so much. And by the way, like all the authors and presenters, like there are questions coming up in Slack and discussions. Please sort of continue there. With that,
thanks a lot.
Let's move on to our third and final talk of the session. It's on the paper Efficient Sparse Collective Communication, and its application to make distributed deep learning faster. And it will be presented by Jiawei Fei, who is a PhD student at National University of Defense Technology, and who is currently visiting a student at KAUST. Jiawei works on accelerating distributed machine learning system by maximizing effective network bandwidth. Yeah, let's get started.
Hello, I'm Jiawei. Today, I'm going to present our work, Efficient Sparse Connective Communication and its application to accelerate distributed deep learning. To begin with, nowadays, people train DNN models to solve problems like image classification or language translation. And it's very time-consuming to train these models, not to mention they are getting even larger. For example, Microsoft released the Turing Natural Language Generation Model, which contains 70 billion parameters and is way too big to train on one single GPU. So we need distributed training to scale out. Let's firstly take a look at how distributed training works. Assuming data parallel, in data parallel mode, each worker keeps a local copy of the DNN model. In each iteration, workers train model on different data subsets. The result of the computation is the model updates. Before the next iteration, workers need to synchronize parameters. There are two ways to do this operation. One is to use parameter servers, and the other is to use connective operations like ring or reduce. It's known that distributed training is usually bottlenecked by communication of model updates among workers. Here we measure the scalability of 6 real-world training workloads. The y-axis shows the scaling factor defined as follows. For the scaling factor, higher is better. From this figure, we can find the scaling factor decreases when increasing node number. This is because of increasing communication overheads. We also find that huge models like DeepLight, LSTM, NCF, and BERT scale very poorly. To understand the communication overheads, we analyze the gradients of different models. Here, table shows the model size and the gradient sparsity. For some large models like DeepLight, LSTM, and NCF, their gradients are highly sparse. This is because they all have large sparse embedding layers. BERT also has a large embedding layer, but its large transformer layers have dense gradients. So its gradient sparsity is low. We observe that one reason that the communication becomes a bottleneck is the inefficiency of exchanging sparse model updates. What do people do to solve this problem? First, in a more generic view, accelerating connective operations would help. However, existing connective libraries do not exploit the sparsity of the data. For example, I'm showing the first step of ring OnReduce algorithm here. One can observe that no matter how many zeros there are in a chunk, a worker needs to send it to its neighbor. This causes suboptimal bandwidth usage. In addition, some sparse connective algorithms are proposed to solve this problem, but we find that they are inefficient. Firstly, alligator-based algorithms have poor scalability. Secondly, current sparse algorithms only support sparse format inputs, representing non-zero values as key value pairs, which causes format conversion overheads for dense inputs. Thirdly, we find current sparse algorithms need high data sparsity. Finally, because the indices of non-zero elements across all workers are unknown before the OnReduce operation, the result can only be broadcast after all the key value pairs are received and reduced. This problem makes current sparse connective works unable to take full advantage of inbound and outbound bandwidth at workers. OnReduce does not have these limitations and achieves the following goals. First is the high performance and scalability. OnReduce can scale better than previous approaches fundamentally. The second is data format universality. OnReduce does not require data to be sparse to provide benefits. The last is the flexibility. The aggregator in OnReduce can run on dedicated server resources or collocated on worker nodes or with the aid of network switches as an in-network aggregation component. OnReduce is designed as follows to achieve these goals. Coordinated aggregation. OnReduce has one component called aggregator to coordinate workers, making them only send non-zero blocks. Blockwise method. It makes OnReduce be able to take full advantage of bandwidth, fine-grained parallelism, and data pipelining. With this, OnReduce can achieve streaming aggregation. Block-based sparsification. It is a compression method for dense gradients, both server-based and in-switch implementation. So, how do we exploit the sparsity? Here we use an example to introduce our basic algorithm. In this example, we have two workers. Each worker has a tensor to be OnReduced. The block size is 2, and the white blocks refer to the 0 blocks. In this particular example, worker 1 and worker 2 are sending block 1. The aggregator receives updates from the worker 1 and worker 2. It can conclude at this point that the updates for this block is ready because worker 1 and worker 2 both have bigger next block index. It can then broadcast the update with next block index 2. The same procedure goes on this time, only worker 1 has non-zero block 2 and sends its block 2. Similarly, the aggregator broadcasts the update with the next block index 3. Finally, worker 1 and worker 2 sends block 3. Note that worker 1 and worker 2 now have infinity next block index, indicating it has transmitted all its non-zero blocks. After receiving the block 3, the aggregator broadcasts the last block with infinity next block index. And when a worker receives infinity next block index, the worker knows the aggregation process is done. This is OnReduce basic algorithm. For the basic algorithm, there is one problem: which block size we should choose. So here is an example. From this example, we can see that small block size increases the block sparsity, while large block size increases the bandwidth usage. So how to balance the trade-off between block sparsity and bandwidth usage is a challenge. To address this challenge, we propose block fusion method. The key idea is to use small block size and a large package size. Here we use an example to show how it works. The number in each block refers to the block index, and the white blocks are 0 blocks. The package consists of 3 parts: block number, block data, and the next offset. Assuming we view the data in 4 columns, firstly, we connect the non-zero blocks in each column and put them into the block data field of the package. As we have 4 non-zero blocks, the block number should be set to 4. After that, we will find the next block offset for each column and put this next offset in the next offset field. With the block fusion method, we can use small block size to get high data sparsity and use large packet size to get high bandwidth usage. However, what can we do when the gradients are not sufficiently sparse to begin with? Let's review the gradient sparsity of the benchmark models. It is easy to see that models like DeepLight, LSTM, and NCF can benefit a lot from OnReduce as their gradients are very sparse. However, for BERT, which is also very large, its gradient has little sparsity. Previous work in the literature has proposed gradient compression methods to generally solve the communication bottleneck by reducing the communication data volume. However, OnReduce cannot benefit from these compression methods because they operate in an element-wise fashion, whereas OnReduce adopts a blockwise design for efficiency. To solve this problem, we extend several existing element-wise specification techniques to block-based ones. Let's take a block top K as an example to show how it works. The block size we use is 2, and the key value is 3. The original tensor has 5 blocks. Firstly, we sum the value of each block. After that, we only keep top 3 block and set the other blocks to 0. And then we set the elements in 0 blocks to 0 and get the compressed tensor. With block-based specification methods, OnReduce can accelerate the distributed training process even for dense models. We implement OnReduce for different environments. OnReduce supports DBDK, RDMA, and GDR. We integrate OnReduce with Pytorch distributed package and Horvath. The aggregator component can run on dedicated server resources or run collocated on worker nodes or run on Tofino switch as an in-network aggregation component. We evaluate OnReduce from the following aspects. Does OnReduce perform better than other dense or sparse connectives? Does OnReduce accelerate distributed training? We also analyze the sensitivity of block size sparsity and non-zero block overlap. Our evaluation setup is as follows. We compare OnReduce with the latest dense connective libraries. Here, figure shows that dedicated OnReduce is better than Nico at any sparsity level, and the collocated OnReduce outperforms Nico when sparsity is more than 60%. We also compare OnReduce with other sparse connective algorithms. We can find that OnReduce outperforms all other sparse algorithms at any sparsity. For end-to-end experiments, we measure speedups related to Nico for training different DL models. The results show that for large and sparse models like DeepLight, LSTM, and NCF, OnReduce has very high speedups, up to 8.2 times at 10 gigabits per second network and 2.9 times at 100 gigabits per second relative to Nico. We also evaluate the end-to-end performance of OnReduce in a multi-GPU, multi-node cluster, which is provided by the Meituan company. The results show that OnReduce can also improve training throughput up to 2.6 times in this setup. To summarize, OnReduce accelerates training up to 8.2 times with real-world workloads. OnReduce demonstrates streaming aggregation for sparse OnReduce with 3 key advantages: high performance and scalability, data format universality, flexibility. OnReduce can also use blockwise gradient compression methods. We have open sourced OnReduce and we want everyone to use and contribute. Thank you for listening.
Thank you for a great talk. And in addition, we also have Elton who can also answer questions regarding this work. I can start. One of the things that I was thinking, like how easy it is for someone to use this. Like, is it completely drop in, or I have to actually know something about my job before I try to do it, or what? Like, is it just because I was just looking up the implementation section, it says that it's merged with PyTorch distributed. And after that, I can just throw any training job and it will automatically figure things out? Or as a user, of machine learning training do I need to know something more about my job to use it?
Yeah, we have integrated the OnReduce into the pre-auto distributed package. So you do not, the users do not need to change the code. You write the distributed code. You just change the backend to OnReduce, and then they will do the OnReduce with OnReduce. It will does this. The only difference is that maybe you need to launch the aggregators firstly, and then you run your distributed scripts, training scripts. Yeah, so it is easy to use. Yeah.
Got it. And another question from Aditya on Slack is, from your performance result, what is the reason for limited speed up for ResNet BART VGG as opposed to other models?
Yeah, because OnReduce is optimize the sparse data OnReduce operation. So for ResNet, VGG and BERT, we have shown the sparsity of their gradients, and it shows that their gradients are dense. So so for OnReduce, it cannot get a good performance. Maybe it will not hurt the performance, but it cannot be better because it needs to benefits from the sparsity. Yeah.
Got it. Thank you. And let's do one last question. So I was thinking sort of how does it, or I mean, maybe whether at all, does it matter what type of distributed training I'm using, if it's data parallelism versus pipeline parallelism, or like some other type of parallelism? Is there any relationship, or it doesn't matter, or it's specific to model parallelism? Like when or when cannot I use your solution?
Yeah, actually, we accelerate the OnReduce operation. So if you want to run, model parallelism, and in model parallelism, maybe you still need the connective, the connective operations. So it can still accelerate this operation if the data you OnReduced or other if your OnReduce is sparse, you can also benefit from the OnReduce. Yeah. Okay, so it is not only the data parent. Yeah.
Yeah. Thank you so much. We have so that's the end of the session, but I have like one more thing before everyone leaves. That's we have about 10-12 minutes. So we are probably going to try and have a very short panel on sort of in general the state of networking for ML and what are the grand challenges. So all these speakers, if you are still around and online, please turn on your camera so we can see you, and I guess feel free to turn the mic on as well. I'm guessing we are not going to speak over each other anyway. And for the others, if you want to move on, the next session is going to start, I believe, at 3:35. So please come back for that one on the big picture. It's a very broad topic. But for us, we are going to talk a bit more about sort of what are the big challenges that the networking community should be sort of focusing on going forward. Say, I mean, to move it more concretely from a student's perspective, say a student in networking, they want to do networking for ML, and what are the problems they should start thinking about, say, to submit to SIGCOMM'23. 22 is too close. So it's like they have 18-month time. And then what would they sort of focus on? What are the big challenges, like from your different perspectives? Because each of you did hardware and software and algorithms, so everyone has different viewpoints. And I'm just very curious to know what are the big challenges that you feel are in front of us. So Mania is a faculty, so I'll pick on her. Yeah, please go ahead.
Thanks, Musharraf. It's a really insightful question. And I guess maybe I want to hear your thoughts on this too. But one question that I keep thinking about is how to design a cluster that is specifically serving ML workloads. And in particular, we just use data centers as our ML, say, training clusters. Data centers have certain properties. They use a fat tree topology. They have ECMP load balancing. They have schedulers. And so is there anything different that we need to do on the network design if we do know that the workload is just, say, ML training or ML inference?
I thought like your paper is trying to address that CPML. It's like you are only trying to do ML training and you want to sort of make sure that you can use high-speed optical networks. And I guess like one thing I would add, maybe like the ultimate goal is to design balanced hardware setup. So there is not just the network, because network being too fast is also basically pointless if it's faster than the total compute. So everyone has to sort of run at roughly equal speed so that there is essentially no bottleneck, or everyone is the bottleneck because everyone is working all the time. And that, I guess, is the grand challenge of any hardware design and system design. And yeah, I mean, it's a very hard problem, and I don't really have any obvious, answer on how to go about it. But I do agree with you. I mean, if we focus on that, this is only going to do machine learning training, or only going to do inference, or only maybe hyperparameter tuning, or I don't know, some other thing that may be needed, or maybe data preparation. I mean, some people would call them, they're just typical big data cluster where you just process data. But still, for each of them, how would we go about sort of changing hardware and optimizing them further? Yeah, I think that is a very interesting topic, but still it seems like very, very large agenda that's like good for, I guess, at a faculty. For you, it's good to think about, but it's now think of a student, what they can actually handle in like, 12 to 18 months. And I promise I'm not farming problems for my students. No one is working at this point right now on this particular topic. So feel free to, share your thoughts. And I mean, everyone else, please chime in, like, don't feel, that you have to just listen in. I feel like students often have better ideas than faculty because we are jaded with too many things in life. And research. Mohammed is laughing.
No, I mean, I think it's just, I mean, I also would love to hear from the students, but one thing I guess I would add is, I think a lot of the problems that we naturally think about are kind of about the high end, like the SIPML paper that, for example, we presented, it's like advancing the very high end, right? If you have 1,000 GPU cluster, I think a lot of interesting problems, particularly from a networking perspective, are going to be in this sort of edge computing world, and trying to actually do sort of efficient ML on low-end devices, and how can the network help with that? Like, what does distributed learning on low-end devices really look like? There's a lot of sort of these questions, like challenges around privacy, challenges around performance, and I think the network has a big role to play there. It's actually inherently more like it's very natural that you're going to get a lot of kind of like networking and communication problems there, just because it's the low end, resources aren't as plentiful. And any communication actually becomes a big bottleneck and incurs a lot of cost. So I would say that world is also something to keep in mind and look for problems in.
Thank you. Anyone else want to add something? And I just have been told that we have to wrap up by 2-3 minutes. So yeah, I wish we could have like hours on this. Like you'd enjoy like talking on very specific thing. And this is something I guess like we should figure out like how to use gather and gather around. I mean, everyone else, anything to add? So I can add one thing, like while you were thinking, is I feel like somehow like energy should come into the play. Like all these AI and ML. Maybe it's not at the edge, but at the level of cloud, actually edge could be as well. Like there is a lot of they are burning a lot of energy. I'm pretty sure electricity to run all these GPUs, and this 1,000 GPU cluster probably needs a lot of megawatts. And how can we sort of optimize? Sort of co-design, not just the communication, but the compute and how much energy they are going to get. And if you have a deadline, when do you have to finish? Do you move things around in time and not do things sort of right now? Because maybe like this energy peak demand and the price is high. I believe like when I was a student back in the days in SIGCOMM 2010 or something, there was a paper on this electricity scheduling in SIGCOMM, like someone from MIT did that. And at that point, like, I mean, who would care? And now I feel like, I mean, the way these the GPUs and everything else is running, and so many of them, we need to sort of actively consider how can we consider energy and how it affects networking and system design and everything else. I mean, yeah, this is something we've been recently thinking about, sort of how to bring energy as a first-class resource as a constraint into sort of all the optimizations that we do in network and systems and other types of schedulers. Guys, you need to, like, I don't know, say something, please. Yeah,
so maybe,
yeah,
cool. So I think I have one point to ask. So it's kind of like related to my research right now. It's like, so like, I think like in the system world, most of people like previously mainly focus on data parallel training, but I feel like the models are getting larger and larger, and more models are required to use like model parallel training. And I think that is way much more complicated world compared to data parallel training, especially for the like communication patterns in those kind of models. So I think like that would be a good like research direction in the future.
Thank you so much. I mean, I'll have to cut it short. There is a link for the Gather, so we can try to congregate there if people are around. But again, thank you so much for your time. I really enjoyed reading the papers, listening to the talks and the answers, and hopefully we'll be in person next year, and we'll have a lot of time to go outside and talk a lot more about this over dinners and breakfast. Thank you so much, everyone.